Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine ABCD constants of a three-phase medium length transmission line based on its nominal pi equivalent circuit. We shall also learn how to calculate percentage voltage regulation and efficiency of transmission of this line using those constants. Using nominal pi method, we have to determine the efficiency of transmission and the percentage voltage regulation of a three-phase 50 Hz 150 km long overhead transmission line delivering 20 megawatts at a power factor of 0.8 lagging at 66 kilovolts to a balanced load. Each conductor has resistance of 0.075 ohm per kilometer and 1.5 centimeter outside diameter, spaced equilaterally 2 meters between centers. Let us first write down the given data. Power delivered to the load PL equals to 20 megawatts, that is equal to 20 into 10 to the power 6 watts. Line to line receiving end voltage VR line equals to 66 kilovolts, that is equal to 66,000 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 66,000 divided by root 3, that gives us 38,105 volts. Given load power factor cos phi L equals to 0.8 lagging. Now we shall calculate power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. We know that power delivered to the load PL equals to root 3 times VR line into IL cos phi L. Therefore, load current IL equals to PL divided by root 3 times VR line into cos phi L. Using values we get 20 into 10 to the power 6 divided by root 3 into 66,000 into 0.8, that gives us 218.7 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 218.7 ampere at an angle minus 36.8699 degree. Here load current IL equals to receiving end current IR. Given length of the transmission line D equals to 150 kilometers. Diameter of the conductor D1 equals to 1.5 centimeter. Equilateral spacing between conductors D2 equals to 2 meters, that is equal to 200 centimeters. Now we shall calculate radius of the conductor. R equals to D1 by 2, that is equal to 1.5 divided by 2, that gives us 0.75 centimeter. Expression for inductance per kilometer per phase L1 equals to 0.05 plus 0.2 into log of D2 by R millihenry. Using values we get 0.05 plus 0.2 into log of 200 upon 0.75 millihenry, that is equal to 1.1672 millihenry. Now we shall calculate inductance per phase L equals to L1 into D. Using values we get 1.1672 into 150, that is equal to 175.1 millihenry or 0.1751 Henry. Expression for capacitance per kilometer per phase C1 equals to 1 upon 18 into log of d2 by r microfarad. Using values we get 1 upon 18 into log of 200 upon 0.75 microfarad, that gives us 0.0099455 microfarad. Now we shall calculate capacitance per phase C equals to C1 into D. Using values we get 0.0099455 into 150, that gives us 1.4918 microfarad or 1.4918 into 10 to the power minus 6 farad. Given resistance per kilometer per phase R1 equals to 0.075 ohm. Now we shall calculate resistance per phase R equals to R1 into D. Using values we get 0.075 into 150, that gives us 11.25 ohm. We have computed inductance per phase L equals to 0.1751 Henry and capacitance per phase C equals to 1.4918 into 10 to the power minus 6 farad. Now we shall compute inductive reactance per phase XL equals to 2 pi F into L. Given supply frequency F equals to 50 Hz. Therefore, XL equals to 2 pi into 50 into 0.1751, that gives us 55 ohm. And capacitive susceptance per phase BC equals to 2 pi F into C. Using values we get 2 pi into 50 into 1.4918 into 10 to the power minus 6, that gives us 468.663 into 10 to the power minus 6 mho. Now we shall determine series impedance per phase of the transmission line. Z equals to R plus JXL, that is equal to 11.25 plus J times 55 ohm. This may be written in polar form as 56.1388 ohm at an angle 78.44 degree. Shunt admittance per phase Y equals to J times BC, that is equal to 0 plus J times 468.663 into 10 to the power minus 6 mho. This may be written in polar form as 468.663 into 10 to the power minus 6 mho at an angle 90 degree. We have obtained series impedance per phase of the transmission line Z equals to 56.1388 ohm at an angle 78.44 degree and shunt admittance per phase Y equals to 468.663 into 10 to the power minus 6 mho at an angle 90 degree. Now we shall calculate Y into Z. Using values we get 468.663 into 10 to the power minus 6 at an angle 90 degree into 56.1388 at an angle 78.44 degree, that gives us 0.02631 at an angle 168.44 degree. This may be written in Cartesian form as minus 0.0258 plus J times 0.0527. Now we shall compute 1 plus 1/4 of y into z, that is equal to 0.99355 plus j times 0.0013175. This may be written in polar form as 0.99351 at an angle 0.076 degree. For pi equivalent circuit, A equals to D equals to 1 plus half of y into z, that is equal to 0.9871 plus j times 0.002635. This may be written in polar form as 0.9871 at an angle 0.153 degree. B equals to Z, that is equal to 56.1388 ohm at an angle 78.44 degree, and C equals to Y into 1 plus 1/4 of Y into Z. Using values we get 468.663 into 10 to the power minus 6 at an angle 90 degree into 0.993551 at an angle 0.076 degree. That gives us 465.62138 into 10 to the power minus 6 mho at an angle 90.076 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 38,105 volt at an angle 0 degree. We have computed receiving end current IR equals to 218.7 ampere at an angle minus 36.8699 degree. For pi equivalent circuit, we have obtained A equals to D equals to 0.9871 at an angle 0.153 degree. B equals to 56.1388 ohm at an angle 78.44 degree, and C equals to 465.62138 into 10 to the power minus 6 mho at an angle 90.076 degree. Let us now calculate sending end voltage per phase. Vs equals to A times VR plus B times IR. Using values we get 0.9871 at an angle 0.153 degree into 38,105 at an angle 0 degree plus 56.1388 at an angle 78.44 degree into 218.7 at an angle minus 36.8699 degree. That gives us 46,798.697 plus J times 8,247.04 volt. This may be written in polar form as 47,519.8 volt at an angle 9.9943 degree. Now we shall calculate sending end current per phase. Is equals to C times VR plus D times IR. Using values we get 465.62138 into 10 to the power minus 6 at an angle 90.076 degree into 38,105 at an angle 0 degree plus 0.9871 at an angle 0.153 degree into 218.7 at an angle minus 36.8699 degree. That gives us 173.0248 minus J times 111.3232 ampere. This may be written in polar form as 205.7436 ampere at an angle minus 32.757 degree. On no load, receiving end current IR equals to 0. Therefore, receiving end voltage per phase on no load VRO equals to Vs divided by A. Using values we get 47,519.8 at an angle 9.9943 degree divided by 0.9871 at an angle 0.153 degree. That gives us 48,140.817 volt at an angle 9.8413 degree. Now we shall determine voltage regulation, that is equal to VRO minus VR divided by VR. Using values we get 48,140.817 minus 38,105 divided by 38,105. That gives us 0.2634 per unit or 26.34%. We have computed sending end voltage per phase Vs equals to Vs at an angle delta equals to 47,519.8 volt at an angle 9.9943 degree, and sending end current Is equals to Is at an angle minus phi 1 equals to 205.7436 ampere at an angle minus 32.757 degree. For star connected system, line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 47,519.8, which is approximately equal to 82.3 into 10 to the power 3 volts or 82.3 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 9.9943 degree plus 32.757 degree. That gives us 42.7513 degree. Now we shall calculate sending end power factor. Cos phi s equals to cos of 42.7513 degree. That gives us 0.7343 lagging. Now we shall compute sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 47,519.8 into 205.7436 into 0.7343. That gives us 21.5375 into 10 to the power 6 watt or 21.5375 megawatt. Let us now determine efficiency of transmission. Eta T equals to PL divided by PS. Given power delivered to the load, PL equals to 20 megawatts. Therefore, eta T equals to 20 divided by 21.5375. That gives us 0.9286 per unit or 92.86%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learnt how to determine ABCD constants of a three-phase medium length transmission line based on its nominal pi equivalent circuit. We have also learnt how to compute percentage voltage regulation and efficiency of transmission of this line using those constants. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.